Before starting our first case study, let us look at bootstrapping technique for sampling. Bootstrapping is a very common technique and is widely used to collect samples from larger datasets and create an approximate normal distribution. Essentially, we'll be collecting samples without replacement. Since this technique is so pivotal in many of the modern statistical analysis, I've decided to include it in the start. So I will start by creating a sample dataset about reviews of a website. And let us say we are interested in determining information on website reviews and page reviews. So let's say we have collected some information day-wise for counts of reviews received. Furthermore, we have a hypothesis, let's say, or our initial assumption that the reviews for our website are gradually decreasing over a period of time. To go about it, I'll be using pandas for this small example. So I will first import NumPy as NP. I will import pandas library as PD, and then I will simply use the read Excel function to read the reviews XLS file. Now this file is small and we can read it in memory. Then I'm using the head function to display the top 5 rows. So as you can see, the data set is very simple. There are only 3 columns: day, reviews, and page reviews. We will be only interested in the reviews column. So effectively, this is a univariate analysis. So I will select rows within the first 100 days and the first 500 days and try to see a decrease that supports my assumption. Obviously, I'm using pandas data frame indexing operations for this purpose. So for example, I've taken the entire data set and I'm saying that give me the rows where the index is less than 101, and in the second line where it is less than 500 and is greater than 100. So basically between 100 and 500 range. In the second line here, I'm just doing a simple average. So I'm just dividing the sum by the length of the vector. Similarly, in the second line of this particular script, I'm doing the same average operation. Now, the mean does look very similar. So the overall mean of first 100 days is 65.01, and the mean of the largest sample from 100 to 500 days is 66.08. So this doesn't tell us much. Let's investigate further. Then I'll create my bootstrap script. I will make lists to hold sample means, and I will keep the number of bootstraps to be 35, and I will use random choice to basically select rows randomly. This is a built-in NumPy operation. NumPy random choice selects n number of random rows, and then we take the mean of the sample and we collate it with other mean values. So basically, for every iteration, just randomly pick 10 rows, put it in sample means, append the list, and so on. So this goes on for 35 times. And the output chart is a bell-shaped Gaussian normal chart which shows mean value around 66. 66 is basically our estimator, and the variation around the mean is called standard error or standard deviation of sample. Now this plot has a very particular shape and is actually called a bell-shaped Gaussian or normal distribution curve. The reason why we get this curve mostly after applying bootstrap sampling even to non-normal distributions is due to something called as central limit theorem. This is a fundamental concept in statistics, the central limit theorem (CLT). In layman terms, basically it means that as the sample size increases on any distribution, the overall average or estimate of your observation approaches a normal curve distribution. Basically, central limit theorem allows us to use the average formula, the one we are so familiar with in most situations. So similarly, I can do this. I can apply the same script on a smaller data set of 100 length, which we created earlier here, where I took only the first 100 reviews, 100 rows, and once again I will take my sample mean list. I will do a bootstrap this time for only 15 times, and once again it will. I will do a random choice. I'll select 20 random rows. I will take the mean. I will append it to the sample means list, and then finally I will use the SNS distribution plot to plot the curve. And as you can see, the mean value is again similar to the earlier larger data set, which was around 65, 66, and this is around 65. So definitely, there's a change across time in our reviews. To investigate it further, we can create a simple density plot of the entire data set. And what we will get is this bimodal distribution. So here we have two peaks. You can think of them as two center of gravities on a mass, which one is around 20 and one is around 60 or 65. Basically, this data set. So what that tells us about this particular column or vector is that the later half of the data is more closer to the 20 value than the 65 value. And actually, we can confirm it using a t-tests. Now, t-test is used to confirm our initial hypothesis. Is, is either to confirm or reject. So we can use we can use the ilog function of Pandas indexing toolkit to get the last 100 rows and then the first 100 rows using colon 100. And then from Skippy, I can import the stats module, which conveniently provides me with the t-test function. So all I have to do is provide the first two arguments as the first 100 rows and the last 100 rows. And the output will give me the test statistic and the p-value. So at 95 confidence interval, if the p-value is less than 0.05, we can confirm, we can reject our initial hypothesis and confirm that indeed there is a difference um, in the last 100 rows as compared to the first 100 rows. So all in all, we can say that the reviews have decreased drastically in the last 100 rows, and the value may be somewhere around 20. So let's summarize what we have done so far. Uh, we had the original problem of investigating whether the reviews have dropped or not. Um, we tested our counts to different periods. For example, we took the first 100 rows, the last 100 rows, and so on. And then we compared them using a statistical test. Now, I use the term hypothesis a lot. A hypothesis is just a proposed explanation for a phenomenon. So, for a scientific hypothesis, it must be testable and falsifiable. And thus, the scientific method requires that one test it and either reject or accept the hypothesis based on the observations. In most practical examples, the true mean estimates are never known, so statistical hypothesis testing is a method to deal with randomness and probabilities of events that we are trying to test. There are several other testing methods besides t-test, but t-test is one of the more widely used